What are the rules for multiplying and dividing fractions?
As to be expected, there are rules for multiplying and dividing fractions. Multiplication of fractions is very straightforward, just multiply the numerators and denominators. Then simplify the resulting fraction, if needed, or if you can. For example, 2/5 x 4/7 equals 2x4 slash 5x7 equals 8/35. This number can't be simplified. Division of fractions entails one main rule: you need to flip over, or invert, the divisor fraction. The fraction on the bottom, to get the result. This is also called the reciprocal of the fraction, see below. Here are the steps. First, change the division sign to a multiplication sign after inverting the fraction to the right of the sign. Multiply the numerators and denominators, and write the result. You can then simplify or reduce the fraction if needed. For example, 1/2 1/4 equals 1/2 x4/1 equals 4/2. This number can be simplified to 2.
What is a series?
A series is closely related to the sum of numbers. It is actually used to help add numbers, therefore. In a sequence it can be the indicated sum of that sequence. In general, the idea is to start with a number, then do something to that number to get the next number. Then do the same to that number to get the next number, and so on. For example, a finite series with 6 terms is 2 plus 4 plus 6 plus 8 plus 10 plus 12. In which 2 is added to each number to get the next number.
What is the standard deviation?
The standard deviation is considered by some to be the second most important statistic, or statistical measure. In the field, it is the measure of how much the individual observations are scattered about the mean. In general, the more widely values are spread out, the larger the standard deviation. For example, if the test results for 2 different exams taken by 50 people in a geology class range from 30 to 98% for the first exam and 78 to 95% for the second exam. The standard deviation is larger for the first list of exams. This spread dispersion of a data set is calculated by taking the square root of the variance.
What did Blaise Pascal invent that eventually caused his interest in math to wane?
French mathematician and philosopher Blaise Pascal. 1623 to 1662, devised the Pascaline in 1642, when he was only 18 years old. He had it built by 1643. This device was possibly the first mechanical adding machine used for a practical purpose. he built it with his father, a tax collector, in mind to help him with the tedious task of adding and subtracting large sequences of numbers. But the device was not very helpful for a variety of reasons. Especially since it used base 10 and did not match up with divisions of the French currency. Other reasons for its rejection are familiar to every century. The device was much too expensive and unreliable, along with being too difficult to use and manufacture. Eventually, Pascal's interest in science and mathematics waned. In 1655 he entered a Jansenist convent, studying philosophy until his death.
What are logical operators in truth tables?
Logical operators in truth tables include such words as and or, which are all represented by certain symbols. For more about logical operators in predicate calculus, see below. For example, and, also called the conjunction operator, is also referred to as a binary operator. It is one of the most useful logical operators, as in P and Q, represented by the symbols // or and. The or, also called the disjunction operator, is also a binary operator. As in P or Q, and represented by the symbols V and. The not, also called the negation or inversion, operator is known as a unary operator, and is represented by the symbols or. In computer programming, not is often represented by the. But note, not all logical operators seem to represent words the way we are accustomed to using them. And many times they seem to contradict their proper definitions. But in a truth table, the logical operator means what it means without the usual nuances of our English language.
What culture took the first steps toward timekeeping?
Around 5,000 years ago, the Sumerians in the Tigris-Euphrates Valley, today's Iraq, appear to have had a calendar, but it is unknown if they truly had a timekeeping device. The Sumerians divided the year into months of 30 days. The day was then divided into 12 periods, each corresponding to 2 of our modern hours, and the periods into 30 parts, each corresponding to 4 of our minutes. Overall, many researchers agree that the Egyptians were the first serious timekeepers. Around 3500 BCE, they erected obelisks, tall, four-sided monuments, placing them in specific places in order to cast shadows as the sun moved overhead. This thus created a large, crude form of a sundial. This sundial time was broken into 2 parts, before noon and after noon. Eventually, more divisions would be added, breaking down the time units even more into hours. Based on the length of the obelisk's shadows. The huge sundials could also be used to determine the longest and shortest days of the year.
Was mathematics always based on a logical foundation?
No, not all of mathematics was always based on a logical foundation. But some ancient cultures did develop certain aspects of logic in their thought. The Greeks were probably one of the first cultures to understand logic's role in mathematics and philosophy. And they studied the subject extensively. For example, geometry, as presented by Greek mathematician Euclid. c. 325–c. 270 BCE, had some foundations in logic. Greek scientist and philosopher Aristotle's, 384–322 BCE. Rules for syllogisms were also based on logic, and he wrote the first systematic treatise on logic. But his logic works were based on ordinary language making, them a matter of interpretation and subject to ambiguities. It was not until the development of calculus that most of mathematics was put on a logical foundation. By the 17th century, people such as German mathematician Gottfried Wilhelm Leibniz, 1646 to 1716, began to demand a more regular and symbolic way to express logic. Logic truly became a part of mathematics around the mid-19th century. Especially with the 1847 publication of English mathematician George Boole's 1815 to 1864, the mathematical analysis of logic, and English mathematician Augustus de Morgan's 1806 to 1871, formal logic. Thus, mathematics began to encompass symbolic logic with precise rules to manipulate those symbols. See below for more about symbolic logic. Of course, nothing is perfect. Although mathematicians in the late 19th and early 20th centuries hoped it would be. They believed that all of mathematics could be described using symbolic logic and made purely formal. But in the 1930s, Austrian-American mathematician and logician Kurt Gödel, 1906 to 1978, put a damper on such an idea by showing that not all truths could be derived by a formal logic system.
What are triangles and how are they classified?
Triangles, or three angles, are polygons with three sides. A triangle's three line segments, or sides, are joined together at three vertices, endpoints. For all triangles, the sum of a triangle's three interior angles is equal to a straight angle, or 180 degrees. Triangles are classified by either the lengths of their sides, or, more commonly, the measurement of their angles. All triangles have at least two acute angles, but the third angle, which can be used to classify the triangle, can be acute, right, or obtuse. For more about these angles, see above. The types of triangles based on angles are: right triangle, there is one angle of 90 degrees. Acute triangle, all three angles are less than 90 degrees, or the triangle has three acute angles. Obtuse triangle, there is one angle greater than 90 degrees, or the triangle has one obtuse angle. Equiangular triangle, an acute triangle in which all angles are congruent. Or when all three angles are equal. Triangles can be further classified by their sides, as in the following. Scalene triangle, there are no sides and therefore no angles that are equal, in other words, no sides are congruent. Isosceles triangle, two of the sides are equal, congruent, and thus the base angles are equal. Equilateral triangle, when all three sides are equal, congruent.
How do you subtract numbers?
Subtraction is the opposite, or, in set theory, the inverse, of addition. In its simplest form, one whole number is essentially taken away from another whole number. When you subtract numbers, you are answering the question of how many are left. For example, if 23 people leave a building that has 123 people. 123, there would be 100 people left in the building.
What are some non-Hindu Arabic numerals encountered around the world?
Although Hindu Arabic numerals are the dominant numerals used around the world, there are some places in which other number symbols are used. For example, there are Chinese, Japanese, Kanji, Greek, Thai, and Hebrew numerals. The illustration lists some of the ones encountered by world travelers. For more information about numbers, see Math Basics.
What is the algebraic concept of inverse?
Inverses in algebra are operations, or numbers, that undo each other. For example, if 1 multiplies 4 by its inverse, or 1/4, the solution is 1, thus. The rule for multiplicative inverse for x, with x asterisk 0, is 1/x, as in x 1/x, equals 1. In addition, if you add -4 to 4, you get 0, 0, thus, the additive inverse of x is x, as in x plus x equals 0.
What is plane geometry?
Plane geometry is simply the study of two-dimensional figures in a plane. Most mathematicians further define the plane as Euclidean. For more information about Euclidean geometry, see above. It examines such objects as circles, lines, and polygons.
What did David Hilbert propose in 1900?
In 1900, German mathematician David Hilbert, 1862 to 1943, proposed 23 unsolved mathematical problems for the new century, most of which only proved to bring up other problems. By the 1920s, Hilbert gathered many mathematicians called the formalists to prove that mathematics was consistent. But all did not go well as mathematical complications set in. By 1931, Kurt Gödel's incompleteness theorem dashed any more efforts by the formalists by proving that mathematics is either inconsistent or incomplete. For more about Hilbert, see Foundations of Mathematics.
What are some transformations in geometry?
A transformation that keeps a figure's same shape and size, but moves it to a new location, is called isometry. There are several common types of these transformations. Dilatation is the only transformation that does not create equal figures. It means to take a shape and make it larger or smaller, but keep the same proportions. In terms of a circle, a dilatation creates another circle with the same center, also known as a concentric circles. Reflection is similar to what we called a flip in elementary school mathematics, like the flip side of an object. One easy way to see this is by noting one's reflection in a mirror. The figure is on one side of a line and the mirror image on the other. Reflection twice about two parallel lines is synonymous with translation. Reflection twice about two intersecting lines is called rotation. Another type of transformation is rotation. This is simple to understand. In elementary school mathematics it is sometimes called a turn or spin. In this case, one point on a plane remains unchanged while keeping all the distances between the other points the same. Finally, a translation, or glide transformation, is similar to what is called a slide in elementary school mathematics. All the points in the plane move in the same direction and the same distance. Or, the figure slides in a single direction. Translation is also considered to be reflection twice across two parallel lines.
What is numerology?
Numerology is the study of the supposed influence numbers have on human affairs. It is considered an occult art in which numbers are used to reflect the spiritual characteristics of people. In general, numerologists match numbers, such as birth dates, to letters, such as names. Then predict things such as a person's purpose in life, their areas of talent, and even behavior patterns. Numerology charts use the numbers 1 through 9, 11, and 22. The values from birthdays and names are divided so that they equal one of these numbers, with each number indicative of something about the person, such as the life path number, expression number, and so on. Although many people use numerology to make life plans or decisions in their life, and some people claim it does work for them, there is no mathematical or scientific basis for numerology claims.
What is dimensional analysis?
Simply put, dimensional analysis is a way of manipulating unit measures using algebra to determine the proper units for a quantity that is being computed. For example, the units of length over time represent velocity in feet per second. Acceleration is velocity over time. Thus, acceleration will then have units of feet per second, or feet per second squared.
How was the area of a circle first determined?
When it comes to determining the area of a circle, there are many historical claims to this solution. One of the earliest techniques may have been the Chinese comb method, in which a circle is cut into n wedges, each 360/n degrees and each piece identical, with the same area. To see how this works, take the bottom half of a unit circle and cut it into wedges like slices of a pie. Place all the wedges next to each other, with the points up, like the teeth of a comb or animal. Then split the top half of the circle in the same way, putting them next to each other above the other wedges, but this time point the tips of the wedges down. Close the teeth. As n goes to infinity, the shape of the combined wedges approaches a rectangle.
What was the first civilization to use a decimal system of weights and measures?
Between 2500 and 1700 BCE, the Harappa, or Harappan civilization of the Punjab, now a province in Pakistan, developed the earliest known decimal system of weights and measures. For more about decimals, see Math Basics. The proof was first found in the modern Punjab region, where cubical, some say hexahedral, weights in graduated sizes were uncovered at Harappa excavations. Archaeologists believe that these weights were used as a standard Harappan weight system, represented by the ratio 1:2:4:8:1632:64. The small weights have been found in many of the regional settlements and were probably used for trade and or collecting taxes. The smallest weight is 0.8375 grams, 0.00185 pounds, or as measured by the Harappa, 0.8525, the most common weight is approximately 13.4 grams, 0.02954 pounds, or in Harappa, 13.64, the 16th ratio. Some larger weights represent a decimal increase, or 100 times the most common weight, the 16th ratio. Other weights correspond to ratios of 0.05, 0.1, 0.2, 0.5, 1, 2, 5, 10, 20, 50, 100, 200, and 500. There is also evidence that the Harappan civilization had some of the most advanced length measurements of the time. For example, a bronze rod found at an excavation was marked in units of precisely 0.367 inch, 0.93 centimeter. Such a measuring stick was perfect to plan roads, to construct drains for the cities, and even to build homes. An ivory scale found at Lethal, once occupied by the Harappan civilization, is the smallest division ever recorded on any measuring stick yet found from the Bronze Age. With each division approximately 0.06709 inch, 0.1704 centimeter, apart.
What are algebraic equations?
An algebraic equation, as with the equations defined above, is a statement in which two numbers, letters, or expressions are equal. But algebraic equations take this idea even further, most of the time. The objective is to try to simplify the numbers and the one, or more, variables in the equation. These can further be defined as any combination of variables or constants linked together by any operation addition, subtraction, multiplication, division, except division by zero. This type of algebraic equation is often referred to as a polynomial. See elsewhere in this chapter for more about polynomials.
What is a simulation?
A simulation is an imitation of some real event or device. It is often used interchangeably with the word modeling, as in modeling of natural systems. A simulation tries to represent certain features, or behaviors, of a complex physical system based on the underlying computational models of the phenomenon, environment, or experience. Simulations are used to understand the operation of real-world, practical systems. For instance, the modeling of natural systems such as the human body. They can be used to simulate a certain type of technology, such as a new type of airplane, or model an engineering concern, such as the stability of a building during an earthquake. Simulators, interactive, physical devices that simulate reality, are also part of simulation. For example, space shuttle simulators are used to help astronauts understand the intricacies and various scenarios associated with flying the space shuttle.
What is the root of a number?
The root of a real or complex number is a number that, when raised to some exponent, or multiplied by itself the number of times indicated by the exponent, equals the original number. Most people are familiar with square and cube roots. There are actually many other such roots, including the real fourth roots, real fifth roots, and so on, and roots associated with complex numbers. For example, the real fourth roots of 16 are 2 and -2, the real fifth root of -32 is -2.
What is sabermetrics?
Sabermetrics is the study of baseball using objective evidence, such as baseball statistics. It uses scientifically based data and various interpretation methods to explain why teams win and lose. Sabermetrics was taken from the acronym SABR, or the Society for American Baseball Research, and was coined by baseball historian, statistician, and writer Bill James, 1949.
What is considered one of Archimedes' most significant contributions to mathematics?
Archimedes made many significant contributions to mathematics. Though not all mathematicians would agree with the label most significant. But one of his contributions did advance the field of calculus by showing that the area of a segment of a parabola is 4/3 the area of a triangle with the same base and vertex, endpoint, and 2/3 the area of the circumscribed parallelogram. To figure this out, he constructed an infinite sequence of triangles, or wedges, finding the area of segments composing the parabola. He began with the first area, A, then added more triangles between the existing ones and the parabola to get areas of A and A/4, A and A/4 plus A/16, A and A/4 plus A/16 plus A/64, and so on. Based on his iterations, he determined the following, the first time anyone had determined the summation of an infinite series. For more about infinite series, see below. A, 1 plus 1/4 plus 1/42 plus 1/43 plus, equals A, 4/3. Archimedes also applied this method of exhaustion. Not literally becoming tired, but close to it, to approximate the area of a circle, which, in turn, led to a better approximation of pi. Using such integrations, he also determined the volume and surface area of a sphere and cone, the surface area of an ellipse, and many others. His work is considered the first steps toward integration that would eventually lead to integral calculus. For more information about Archimedes and his wedges, see geometry and trigonometry.
How is math used in statistical process control?
Statistical process control, SPC, involves using statistical techniques to measure and analyze the variations within a process. With SPC, industrial engineers monitor, control, and ideally, improve a process through statistical analysis. The four basic steps include measuring the process, eliminating variables within the process to make it consistent, monitoring the process, and Finally, improving the process to make the, usually better, intended product. But it is not the answer to everything. All the SBC does is ensure that the product is being manufactured and designed as intended. Thus, SBC does not tell whether the design is good or bad, just if it's made according to plan.
Did any cultures use more than one base number in their numbering system?
Certain cultures may have used a particular base as their dominant numbering system, such as the Sumerians' base 60, but that doesn't mean they didn't use other base numbers. For example, the Sumerians, Assyrians, and Babylonians used base 12, mostly for use in their measurements. In addition, the Mesopotamian day was broken into 12 equal parts. They also divided the circle, ecliptic, and zodiac into 12 sections of 30 degrees each.
What is division?
The word divide comes from the Latin root vidua, referring to a separation. The word divide shares its major root with the word widow, and di, a prefix that is a contraction of dis, meaning apart or away. In division, the number being divided is called the dividend, while the number dividing it is called the divisor. The end result is called the quotient. For example, in 20/5 equals 4, 20 is the dividend, 5 the divisor, and 4 the quotient. Division in mathematics is a relatively new concept for the masses. It was only taught at university levels after the 16th century. The first to offer division to the public was German mathematician Adam Riese. 1492 to 1559, also seen as Ries, or Ris, in his work Rechnung nach der Länge. Auf den Linehan VND, Sick, Feder, often shortened to Practica. His work reached more people for an important reason, instead of the usual practice of writing a mathematical book in Latin. He wrote his book in German, thus reaching a wider audience.
What is population dynamics?
One major area of interest in mathematical biology is population dynamics. A population is the number of individuals of a particular species in a certain area. Population dynamics deals with the study of short and long-term changes in certain biological variables in one or several populations. Population dynamic studies have actually been around for centuries. For example, weight or age comparisons of human or other animal populations, or even how such populations grow and shrink over time, have long been areas of study. With regard to human populations, the two simplest kinds of input in a population study are birth and immigration rates. And the two basic outputs are death and emigration rates. If the inputs are greater than the outputs, the population will grow. If the outputs are greater than the inputs, the population will shrink.
How did Joseph Marie Jacquard's invention benefit calculating devices?
In the late 18th century, French weaver and inventor Joseph Marie Jacquard, 1752-1834, developed a practical automatic loom that wove patterns into fabric. It was controlled by a link sequence of punched cards. This in itself was a major advance in the production of textiles. But it would also prove to be a boon to calculating devices. Borrowing Jacquard's idea, both Charles Babbage and Hermann Hall Erith, see below, would use such cards on their own computing machines. The company that Hall Erith formed eventually became International Business Machines, IBM. A company that for 30 years promoted and benefited from mechanical punched card processing.
What are prime and composite numbers?
Prime numbers are positive integers, natural numbers, that are greater than 1 and have only 1 and the prime number as divisors, factors. Another way to define a prime number is an integer greater than 1 in which its only positive divisors are 1 and itself. For example, prime numbers less than 20 are 2, 3, 5, 7, 11, 13, 17, and 19. All other integers greater than 1 that are not prime are called composite numbers. There are other rules. The number 1 is unique, and is not considered a prime or composite number. And one of the basic theorems of arithmetic is that any positive integer is either a prime or the product of a unique set of prime numbers. For example, the number 12 is not a prime, but it has a unique prime calculation written as 2x2x3.
Who developed analytic geometry?
Analytic geometry began when French philosopher, mathematician, and scientist René Descartes, 1596–1650, in Latin. René Descartes published a work explaining how to use coordinates for finding points in space. He was the first to make a graph and presented a geometric interpretation of a mathematical function. This marked a step toward what is now known as Cartesian coordinates, a term derived from Descartes' Latin name. Around the same time, an independently French mathematician Pierre de Fermat, 1601–1665, also did much to establish the ideas of coordinate geometry. But, unlike Descartes, Fermat did not publish his work. Both Descartes' and Fermat's ideas would lead to modern Cartesian coordinates. For more about Descartes and Fermat, see History of Mathematics.
What is the difference between the Earth's sidereal and solar days?
The difference between the Earth's sidereal and solar days has to do with angles and the Earth's rotation. The mean solar day is equal to 24 hours, or the average of all the solar days in an orbital year. The mean sidereal day is 23 hours, 56 minutes, and 04.09053 seconds. It is not exactly equal to a solar day because by the time the Earth has rotated once, it has moved a little in its orbit around the Sun. Thus, it rotates for about another 4 minutes before the Sun is considered to be back in exactly the same place in the sky as it was the day before. The actual divisions of geologic time are not arbitrary, or uniform. The larger divisions are based on major events that occurred sporadically over the Earth's long history. For example, the end of the Permian period, about 240 million years ago, was marked by a major catastrophe. Some scientists estimate that close to 90% of all species on the Earth died at that time, resulting in a major extinction event that may have been caused by huge volcanic eruptions or even a space object striking the Earth. The smaller divisions are usually based on specific local structures or fossils found within the rock. Most often they are named after local towns, people, and sundry other nearby associations.
What are economics and econometrics?
Economics is a branch of the social sciences that deals with the production, distribution, and consumption of goods and services, including their management. The application of mathematical and statistical techniques to economics and financial data is called econometrics. It includes the study of problems, the analysis of data, and development and testing of theories and models.
What are rational, irrational, and real numbers?
Rational, or fractional, numbers are most often regarded as divisions, or ratios, of integers. By creating a fraction, dividing one integer by another, a rational number produces either a number that ends or repeats decimals. For example, 1/4 equals the decimal equivalent of 0.25. 1/3 is equivalent to 0.33333. Both of these are rational numbers. For more information about fractions, see p. 98. On the other hand, irrational numbers are all the numbers that can be written as non-repeating, non-finite, or non-terminating decimals. Also called non-rational numbers, they include the decimal equivalent of pi, or 3.141592. Finally, if you put the rational and irrational numbers together, they form the real numbers. Most numbers we use in our everyday lives are real numbers.
What are the major scales used in interpreting hurricanes and tornadoes?
There are two major scales used to interpret hurricane and tornado intensity and thus potential damage. The Saffir-Simpson Hurricane Damage Potential Scale is a hurricane force scale using the numbers 1 through 5 to rate a hurricane's intensity. The scale was developed by engineer Herbert Saffir, 1917, and pioneer hurricane expert Robert Simpson. 1912, in 1971. A number on the scale is assigned to a hurricane based on its peak wind speed. It is also used to give an estimate of the potential property damage and flooding expected along the coast from a hurricane landfall. The Fujita-Pearson Tornado Intensity Scale, or F-scale, is used to measure tornado wind speeds. It was developed in 1971 and named after Tetsuya Theodore Fujita, 1920 to 1998, of the University of Chicago, and Alan Pearson, who was then head of the National Severe Storms Forecast Center in Kansas City. It was Fujita who came up with a system to rank tornadoes according to how much damage they cause. He developed his categories by connecting the 12 forces of the Beaufort wind scale. Knots based on what the sea surface looks like from smooth to waves over 45 feet, with the speed of sound, Mach 1. Then, for each category he estimated how strong the wind must be to cause certain observed damages. Fujita's scale was later combined with Pearson's scale, which measures the length and width of a tornado's path, or its contact with the ground.
Who was Vitruvius?
Marcus Vitruvius Pollio, c. 1st century BCE, was a Roman writer, architect, and engineer. He was the author of De Architectura Libri de Cm, known today as the 10 Books of Architecture. This Latin treatise, dedicated to Octavian, the heir and adopted son of Julius Caesar, was written around 27 BCE. For more about Octavian, see Mathematics Throughout History. Possibly the first works published about architecture, the books entailed a compilation of architectural ideas of Vitruvius's day and covered the following 10 subjects: principles of architecture, history of architecture and architectural materials, Ionic temples, Doric and Corinthian temples, public buildings, theaters, music, baths, and harbors, town and country houses, interior decoration, water supply, dials and clocks, and mechanical engineering with military applications. Specifically, the topics included such forward-thinking ideas as the manufacture of building materials and dyes, material science, machines for heating water for public baths, chemical engineering, amplification in amphitheaters, acoustical engineering, and the design of roads and bridges, civil engineering. De Architectura was wildly successful, and Vitruvius's architectural advice was followed for centuries. But because Vitruvius's books were passed down through the ages, they were copied by various people, especially throughout the Middle Ages. Many medieval engineers added information to the texts, treating the books as handbooks, not documents to be preserved. In the end, historians have had to winnow away the added sections to find the true writings of Vitruvius.
What were some early counting devices?
The very earliest counting devices were human hands, with the fingers used as digits. There were limitations to this device, though, especially since each hand only has 5 fingers. To count more items, some cultures assigned even larger counts to other parts of the body. Such counting methods became tedious, so merchants and others who needed to keep track of assorted items turned to nature, using sticks, stones, and bones to count. Eventually, devices called counting boards were developed. At first, the counting boards were simple, usually entailing drawing lines with fingers or a stylus in the sand or dirt.
What is mathematical biology?
Mathematical biology is another word for biomathematics. The interdisciplinary field that includes the modeling of natural biological processes using mathematical techniques. Mathematical biology is carried out by mathematicians, physicists, and biologists from various disciplines within their fields. These scientists work on such problems as modeling blood vessel formation, with possible applications to drug therapies, modeling the electrophysiology of the heart, exploring enzyme reaction within the body, and even developing models that track the spread of disease.
What is a ruler?
Usually made of wood, metal, or plastic, a ruler is a measuring stick. Most rulers have a straight edge used for drawing straight lines and measuring lengths. The simplest and most well-known ruler has small scales, measured in terms of inches, or centimeters. In order to read a ruler, the user needs to know the main divisions. For example, when looking at a foot ruler, the longest increments are represented by inches and are usually numbered 1 through 12, the measurement starts on the left end of the ruler, which may or may not be marked with a 0. The next divisions, from smallest to largest, are the distances between the smallest increments represent a 1/16 of an inch, the distances between the next largest increments represent an 1/8 of an inch. The next represent a 1/4 of an inch, and, finally, a 1/2 of an inch. For more about measurement, see mathematics throughout history.
What are some statistics used in football?
There are several mathematical statistics used in football. The touchdown percentage is the touchdown passes divided by the pass attempts. The passer, quarterback, rating is determined by 4 elements and their statistical calculations. Percent of completions, average yards gained per attempt. Percentage of touchdown passes, and the percent of interceptions. The average is 1.0, the bottom is 0, and the maximum anyone can receive in any category is 2.375, this is difficult, for a passer to gain 2.375 in completion percents. He would have to complete 77.5% of his passes. Those passers who earn a 2.0 rating or better are exceptional. For example, the National Football League ranks this at 70% in completions, 10% in touchdowns, 1.5% in interceptions, and 11 yards average gain per pass attempt. Rushing is a common statistic commonly heard after any football game on the after-game special. It is the average yards per carry, average, a number measured by the total yards divided by the attempts. In punting, the net punting average, net, is the gross punting yards minus the return yards, minus 20 yards for every touchback, divided by the total punts.
How is mathematics used by search engines on the World Wide Web, www?
A search engine is a program that searches for internet documents, usually on the World Wide Web, using certain keywords. It then returns a list of results in which those keywords are found. Search engines such as Google, AltaVista, and Excite are a general class of programs that use a proprietary search algorithm. They rely on probability, linear algebra, and graph theory to create a list that, ideally, produces the most relevant website results for the user.
They are listed as follows: n indicates natural numbers or integers, x represents real numbers. Z stands for complex numbers. What are some other terms used in dealing with algebraic equations?
There are many terms in algebra, including those dealing with equations. The following lists some of the more common ones. Equality and inequality. An equality is a mathematical statement that shows the equivalence of two quantities. For example, if A is equal to B, it is written as the equality A equals B. An inequality is just the opposite, A does not equal B, or A asterisk B. Formula. A formula is a rule, fact, or principle expressed in terms of mathematical symbols, including equations, equalities, identities, or inequalities. Note, the plural of formula in Latin is formulae, but it has become more readily accepted as formulas. Identity. An identity is a mathematical relationship equating one quantity to another that initially may appear to differ. It also means an equation that is always true, such as the Pythagorean theorem. For more about identities, see below.
How are some economic indicators calculated?
There are many economic indicators that are mathematically calculated, mainly in order to understand a nation's economic health. The gross domestic product, GDP, is the current measure of a nation's economic performance. It is the total market value of all final goods and services produced in a country during any quarter or year. Its calculation includes such variables as total consumer spending, business investments, government spending and investments, and the value of exports minus the value of imports. The Consumer Price Index, CPI, is a measure of the average change over a period of time of prices paid by consumers for a market basket of consumer goods and services. A market basket is based on information from a sampling of consumers on their spending habits, what they put in their basket. There are also the M1 and M2 indicators. The M1 is a measure of the money supply including currency in circulation, such as travelers' checks, deposits, and checking account balances that can be spent immediately. M2 is the M1 plus assets that are invested for the short term, such as certain overnight repurchase agreements, savings deposits, time deposits, less than $100,000, and money market mutual funds. There is also an M3 that relates to the big bucks from places such as lending institutions.
What are the divisions found within the field of geometry?
The geometry field has several distinct divisions, including plane geometry. This includes common features such as circles, lines, triangles, and polygons. Solid geometry. This also includes such figures as circles and lines, as well as polyhedrons. Spherical geometry. This includes shapes such as spherical triangles, see below, and polygons. Analytic geometry, also called coordinate geometry. This includes the study of figures in terms of their positions, configurations, and separations. There are other types of geometry, too, including projective geometry and non-Euclidean geometry. Most of these are more complex forms of geometry that each have their own special reasons for use.
What is a circle?
A circle is one of the most fundamental shapes in geometry and one shape we commonly see every day. For mathematicians, a circle is defined as a set of points on a plane at a certain distance from a center point. In reality, a circle is a polygon with an infinite number of sides. The distance of a line segment from the center to the points on the circle is called the radius, or a line segment whose endpoints are on any point on the circle and its center. A line segment that travels from one endpoint on the circle, through the radius, center of the circle, and to another endpoint directly opposite is called the diameter. 2 times the radius of a circle is the diameter. The outer perimeter of the circle is called the circumference. The chord of a circle is a line segment whose two endpoints are on the circle. Concentric circles are two or more circles that lie in the same plane and have the same center, but with different radii. Circles with the same radius are called congruent circles. For more about circle measurements, see elsewhere in this chapter.
What was the Julian calendar?
By the time of Julius Caesar, 100 to 44 BCE, Roman calendar keeping was a mess. Caesar decided to reform the Roman calendar. Asking help from astronomer and mathematician Sosigenes of Alexandria, lived c. 1 BCE, not to be confused with Sosigenes the Peripatetic c. 2nd century, an Egyptian philosopher. The year 46 BCE would consequently have 445 days, a time appropriately called the Year of Confusion. Sosigenes began the reformed year on January 1, 45 BCE, a year with 365 days, and proposed an additional day for every fourth year in February, leap day. The alternate months of the year, January, March, May, July, September, November, had 31 days, the other months would have 30 days. In the Julian calendar, there was only one rule: every year divisible by 4 was a leap year. The vain heir to Caesar, Augustus Caesar, 63 BCE 14 CE, aka Gaius Octavius, Octavian. Julius Caesar Octavianus, and Caesar Augustus, would change the Julian calendar in several ways. Not only did he name the month of August after himself, but he would change the number of days in many months to their present usage, adding more confusion to the calendar. The Julian calendar would govern Caesar's part of the world until 1582. Not that the Julian year was perfect. A year's 364.25 days was too long by 11 minutes 12 seconds. Although the difference between today's measurement of the year and the Julian year was not great, it adds up to 7.8 days over 1,000 years. But as with many decrees and mandates, Caesar, Sosigenes, and Octavian left it up to future generations to fix the problem.
What movies had mathematics as their primary focus?
The following 3 movies were either about mathematicians or had a dominant mathematical theme. A Beautiful Mind, 2001, based on the book by Sylvia Nassar, also see above. This is Hollywood's version of John Nash's rise, descent into mental illness, and eventual redemption. Directed by Ron Howard, it stars Russell Crowe and Ed Harris. Pi, 1998, this dark, low-budget, black and white film is about a mathematician's obsessive search for patterns in everything. While everyone from Wall Street investors to religious fundamentalists want to find and exploit him. Directed by Darren Aronofsky, it stars Sean Gullett and Mark Margolis. Infinity, 1996, this movie about the early life of brilliant and eccentric Nobel Prize-winning physicist Richard Feynman. 1918 to 1988, is both a tribute to the scientist and a whimsical romance. Directed by Matthew Broderick, it stars Matthew Broderick and Patricia Arquette.
How can I prove that 1 equals 0?
There is a way to show that 1 equals 0. And it includes an interesting proof. Consider two non-zero numbers x and y such that x equals y. If that is so, then x2 equals xy. Subtracting y2 from both sides gives x2 y2 equals xy y2. Then dividing by xy gives x plus y equals y, and since x equals y, then 2y equals y. Thus 2 equals 1, the proof started with y as a non-zero, so subtracting 1 from both sides gives 1 equals 0.
What are the ways to convert between AM and PM and 24-hour time?
When converting AM/PM to 24-hour time for the hours between 12 AM and 12:59 AM. Just subtract 12 from the time. For instance, 12:45 AM minus 12 will equal 0045, and 12:59 AM minus 12 will equal 0059 times between 1 AM and 12:59 PM are a straight conversion. Such as 9 AM equals 0900 and 11 AM equals 1100. For the conversion between 1 PM and 11:59 PM. Add 12, such as 8:34 PM plus 12 equals 2034, and 11:59 PM plus 12 equals 2359, also seen as 2034 and 2359. To convert in the opposite direction from the above, add 12 for the hours between 0000, midnight, and 0059, such as 0034 plus 12 equals 12:34 AM, and 0059 plus 12 equals 12:59 AM. 2. Convert from 0100 to 11:59 and from 1200 to 12:29, there is a 1-to-1 conversion. The former to AM and the latter to PM. For example, 0100 equals 1 AM, 0345 equals 3:45 AM, 1235 equals 12:35 PM. And 1259 equals 12:59 PM. To convert between 1300 and 2359, subtract 12, such as 1424 minus 12 equals 2:24 PM. And 2359 minus 12 equals 11:59 PM. How are local A.M/P.M?
What is a currency exchange rate?
When traveling to another country, it is important to know the currency exchange rate, which is the value of a traveler's home currency compared to the currency of the country being visited. For example, like all currency, the US dollar fluctuates daily when compared to other countries' currencies. If you travel to Canada, and the US dollar can buy $1.40 Canadian dollars, then the exchange rate is 1.40 to 1. If you go to New Zealand, and the US dollar exchange rate is 0.5477, then 1 New Zealand dollar is worth 54.77 US cents.
Was Fermat's last theorem finally solved?
Just before the end of the 19th century, German industrialist and amateur mathematician Paul Wolfskehl, on the brink of suicide, began to explore a book on Fermat's last theorem. Enchanted with the numbers, he forgot about dying and instead believed that mathematics had saved him. To repay such a debt, he left 100,000 marks, about $2 million in today's money, to the Göttingen Academy of Science as a prize to anyone who could publish the complete proof of Fermat's last theorem. Announced in 1906 after Wolfskehl's death. Thousands of incorrect proofs were turned in, but no true proof was offered. But people kept trying and failing. Fermat's last theorem was finally solved in 1994 by English mathematician Andrew John Wiles, 1953. Wiles was offered the Wolfskehl Prize in 1997. By that time, the original $2 million had been affected by not only hyperinflation but also the devaluation of the mark, reducing its value to $50,000. But for Wiles, it didn't matter, his proving the last theorem had been a childhood dream. It is interesting to note that some mathematicians do not believe Wiles uncovered the true proof of Fermat's last theorem. Instead, because many of the mathematical techniques used by Wiles were developed within recent decades, some even by Wiles himself. Wiles's proof, although a masterpiece of mathematics, could not possibly be the same as Fermat's. Still, other mathematicians wonder about Fermat's words in claiming that he had found a proof.
How did Albert Einstein use mathematics?
German-born American theoretical physicist Albert Einstein, 1879 to 1955, is recognized as one of the greatest physicists of all time, but he was also a notable mathematician. In 1905 he developed the special theory of relativity, mathematically demonstrating that two observers moving at great speeds with respect to one another will experience different time intervals and measure lengths differently. That the speed of light is the speed limit for all objects having mass, and that mass and energy are equivalent. By around 1915, Einstein completed a mathematical formulation of a general theory of relativity, this time adding gravitational effects to determine curvature of a time-space continuum. He further tried to discover a unified field theory, which would combine gravity, electromagnetism, and subatomic phenomena under one set of rules, but he, and no one since, has ever found such a theory. For more about Albert Einstein, see History of Math.